everyone. My name is Bing. I'm a software engineer at Slack, working on the infrastructure team, dealing with scalability, resiliency, and performance of the service. Before I start the talk, let me do a quick poll. Raise your hand if you use Slack. I see quite a few hands. Great. I'm really glad you are our users. This is a snapshot of Slack app. Inside Slack, everything is organized by team. Users join a team, they send real-time messages to each other in channels. Channels is a self-selected group of users who share the same interest. Besides sending messages, users upload files, search for content, and install and use apps inside Slack. Slack was launched in 2013, and throughout the 6 years, we grew to 10 million daily active users today. I will show you some numbers that demonstrate the rate of growth. In 2016, we have 4 million daily active users. Our biggest team have 20,000 users. And at peak, we have 2.5 million number of connections simultaneously. This year, we reached 10 million users. Our largest team have more than 400,000 users. That's 20 times more than 3 years ago. At peak, we have nearly 8 million concurrent connections. With the rapid size and scale increase, the question we keep asking ourselves is how to make Slack scale and reliable. How to scale it to 10 times than it is today. There are times in the past where we failed. We provided degraded performance, and how do we prevent it from happening again? Let's rewind time to 2016 and see how Slack worked. There are two important components of Slack. One is web app. It's our HTTP service. It implements all business logic of Slack. Users send HTTP requests to web app and receive response. The other important component is web app. Client connects to it using WebSocket connections. And Messenger Server is a real-time event hub. It gives client updates about real-time events. WebSocket is a duplex communication protocol. It means client and server establish a long-standing connection, and both client and server can push messages to each other. When users connect to Slack, it first sends the RTM start HTTP request to web app. Web app authenticates the user. It sends back a payload of the team, including who are on your team and what channels you are in. It also includes a URL that the client can use to establish the WebSocket connection. While you're connected to Slack, Messenger Server keeps sending updates. That's how you receive messages from your team member when they send out messages. This worked pretty well when Slack was small. Client cached data on its local cache, and then updates trickles in real time through the WebSocket connection. Everything feels fast and real time. On the server side, it is straightforward to implement, and everything is scoped by team. It's pretty easy to scale up. When more teams sign up, we just add more servers. However, things become more interesting when the size and scale keeps increasing. We run into a few challenges. The first challenge, our biggest team keeps growing, and the user experienced slowness when connecting to Slack. The second problem is thundering herd. Connecting to Slack is much more expensive than keep connected. This made Slack especially vulnerable to thundering herd problem. Third, we have hotspot in our database shards. And finally, failures happen all the time in our database. How do we make resilient services in the face of failures? In the past 3 years, we built 3 things that tackles these challenges. I will talk about each one of them. The first challenge is user experienced slowness when connecting to Slack. In the connect flow, the server will send a payload, a a payload of the team to client, and client cache them locally. However, this payload grows with the number of users and channels on the team. When we have a few hundred users, the payload is a few hundred kilobytes, which is great. When we have a few thousand users, the payload is a few megabytes. It is okay, not great. When you are on mobile or have a low networking connection, it can be slow. When the users grows to a few hundred thousands, then it becomes terrible. It's almost impossible for you to connect to Slack in a reasonable amount of time. That's when we introduced client lazy loading. The idea is simple. Download less data upfront and load more data on demand. This requires client to completely rewrite the data access layer. It can no longer make the assumption that data is always available locally. Instead, it needs to load data remotely. While we loading data remotely, there is networking round-trip time. But still, we want users' experience to be seamless and fast. So we decided to build a new service. It's a cache service which caches a bunch of data and deploy it at the edge of the network. So it's closer to user that provides a low latency. We call this service Flannel. You may ask, why the name Flannel? It turned out naming is one of the difficult problems in computer science. On the day when the project was kicked off, our leading engineer were wearing a flannel shirt. That is why. To be clear, Flannel is not a DNS. It uses in-process memory, and it provides a thin business logic on top to allow clients to query objects. It provides both HTTP and WebSocket API. How do Flannel update its cache? It is subscribed to a messenger server. Remember, messenger server is the real-time event hub. So Flannel subscribed to messenger server saying, these are the list of users and channels I'm interested in. Messenger server sends Flannel updates when those objects update. This is very similar to how clients subscribe to messenger server. It tells messenger server, these are the channels that I'm in, sending me new message when somebody posts a message. Flannel works the same way. Flannel is deployed to 10 different regions across globally, and we choose the closest region when serving. We choose the closest region to a user when serving requests. Here is a latency graph. Showed that we migrated some channel membership query from web app to Flannel, and the P99 latency dropped by 2 seconds. This demonstrates Flannel is a low latency query service. So we used the lazy loading to tackle the first challenge, that user experienced slowness when connecting to Slack. Connecting to Slack is no longer expensive. This also helps with thundering hertz problem, because since the connecting is no longer heavy, it can help us with the thundering hertz. I will talk about more resilient measures later in the talk that helps us with thundering hertz. The third challenge is hotspot. We have hotspot in our database because we shard everything by team. What does that mean? We use MySQL as our database. We have a few thousand database servers, and among which one of them is special. We call it main shard. It keeps a mapping of team ID to shard ID. So when you need to query data on team A, you first go to main shard and ask, where is data for team A? Main shard tells you it's shard 1. Then you go to shard 1 to actually access data for team A. This is a very easy sharding schema. And also it provides great failure isolation, because when the shard goes down, it only affects a few teams that are on that shard, and does not affect other teams that are on other shards. However, there are a few drawbacks. First, there is a single point of failure. When the main shard fails, you cannot access any data because you don't know which shard to go to fetch data. Second, there's hotspot. Certain teams are much larger than others, so the shards corresponding to those teams are pretty busier. And third, there are times when a shard becomes really busy that we need to split it to avoid co-locate a few big teams on the same shard, and this process is pretty manual. And finally, we have some new complexity that comes from new features. We launched a feature called shared channels. It means two different teams can share a channel so that users in that channel and content in those channels are shared by both teams. Under team sharding, we can either store data on one side of the team, or we duplicate data on both teams. Neither of them are ideal. The solution is we introduced Vatis. Vatis is an open source project that provides flexible sharding. It is also built on top of MySQL. What does flexible sharding mean? So we no longer shard everything by team. We can choose how to shard based on the usage. For example, for users table, we can shard by user ID. And for channels table, we can shard by channel ID. The application can just treat the hundreds of thousands of database servers as one logical giant big database. And the sharding is handled by Vatis. Vatis also supports cluster management. It knows what is where, and it provides automatically, it can automatically expand the cluster. We're in the process of migrating all our data into Vatis. We are migrating data feature by feature. One feature can involve multiple tables. We first analyze the queries and understand the common patterns. Then we deciding on a proper sharding key. Next, we do write the data to both the old MySQL system and to the new Vatis system. We let it run for a while. We backfill all the historical data, and then we see the new system works fine. Then we flip the switch. Currently, Vatis is serving 20% of all our production traffic, and we're going to spend a few more quarters to migrate everything into Vatis. Now, we use the Vatis to tackle the hotspot problem in our databases. The last challenge is failures. Failures happen all the time in our data center. However, we want to build resilient services in the face of failures. There's an observation made by a guy named Murphy. Things can break in various different ways. When we talk about failures, there are many different kinds. Hardware can fail. Servers can crash, and disks can fail. There can be networking partition. Routers and switches can fail so that one part of the network cannot reach the other part. There's traffic surge that overload our servers. And also there are bugs. We tried our best to prevent bugs from going to production. However, bugs in production is just an actuality. Over the course of 3 years, we adopted 3 different types of resilient measures. The first one is Autoscaling. Autoscaling is a tool provided by AWS. We can scale up and scale down our cluster based on some metrics. The metrics can be CPU usage, memory usage, or packets per second. It can also replace failed servers with new ones. In practice, whenever scaling down Slack's cluster, we will scale up. So this is especially helpful when we have a surge of traffic, and also helpful when our traffic, with organic traffic growth, we just keep expanding the cluster. The second thing we adopted is admission control. We keep track of the number of concurrent requests that come into the service. When there's new requests coming, we increase the count by 1. when the server receives, finishes handling the request, it decreases the counter by 1. And then we use this, if the concurrent request exceeds the limit, then we start to reject the traffic, or we put the incoming request into a queue. By using this, we are making sure that the service always operates under its capacity. So for example, if the server can handle 1,000 requests per second and 2,000 requests are sent to it, it will still serve 1,000 of them and reject the rest of them. There is a drawback of this method. It is very effective to protecting the server from being overloaded, but there is a drawback that you need to set a static limit. How do you know the static limit of your server? You need to thoroughly test it. So in practice, we normally test the servers periodically every few months to know the exact capacity of your server. There's a second way that is more dynamic. You don't need to know ahead of time what's the limit of your server. You just detect CPU or memory usage, depending on whether your server is CPU bounded or memory bounded. And if the CPU or memory usage exceeds the threshold, you can start to reject traffic. This is also effective as the one previously, and admission control combined with auto-scaling is very helpful when there's a thundering herd problem. On one hand, it starts to reject traffic so that servers won't be overloaded by the surge of traffic. In the meantime, auto-scaling kicks in and add more servers into the cluster so it can actually serve more traffic. The third way to build resilient services is regional failover. We have 3 regions in our European that serves European users. If one region becomes unhealthy, then we fail the client traffic to a nearby region. How do we implement it? Inside the region, the frontier, the very first tier, is a load balancer. And behind it, there are tiers of services. Each layer of services, health check, is backend services. If the backend services becomes unavailable, then it marks itself as unhealthy, so that the unhealthiness can bubble up all the way to load balancer. When load balancer detects like half of the backend service is no longer available, then it decides the whole region is unhealthy. Then it sends a notification to our DNS provider saying blocking my IP address so that new traffic will no longer go into this region. This is a great way when we have a full region failures. We also have a second way to do regional failover, which is initiated from client side. This is more helpful when you have partial region failure, or you have localized failure where some users cannot access the region. Let's see how this works. When client connects to Slack, it first asks the DNS server, what is the IP address of wss-primary.slack.com. The DNS server, based on the user's IP address, estimates where you are, and then decide, for example, Dublin is your closest region, so it returns the IP address of Dublin. Client connects to Dublin, but fails. It will make a second attempt. It asks the DNS server, what is the IP address of wss-secondary.slack.com. Similarly, the DNS server, based on the IP address, knows where you are. It finds out Dublin and London are the most closest regions. Then it randomly pick one of them and return the IP address to client. Then client connect to Slack using that IP address. There's a high probability that this time client will reach a healthy region. With 3 retries, there is 87.5% of chance that user will connect to a healthy region. Here is a graph shows client-side regional failover in action. On the bottom left, the purple line shows we lost tens of thousands of connections in our Sao Paulo region. On the bottom right, three regions have a traffic increase: US East, US West, and EU West. This means our traffic in Sao Paulo was automatically failed over to 3 other nearby regions, depending on where the users are. And this process is all automatic. In conclusion, Slack runs into 4 challenges over the course of 3 years. First, user experienced slowness when connecting to Slack. We introduced client lazy loading and built Flannel to enable client to fetch data on demand. This also helped with Thundering Herd problem. Another challenge we had is we had a hotspot in our database. We introduced Vatis that removed single point of failure and also brought uniformed usage among different database servers. And finally, we want to build resiliency services by using Autoscaling, admission control, and regional failover. I'm hoping the experience of Slack can give you some idea about how to scale your own services to 10 times more or even 100 times more. Some of the practices, maybe you can adopt some of those when building your own services. That's all for my talk. Thanks. Now I can take questions.
Does anybody have any questions?
Thanks for the talk. I actually enjoyed it. So one question. All these infrastructure, do analytics also enter in this big picture? Because you described the infrastructure for messaging and so on. But in order to do analytics, I assume that Slack does it some way or another. You also need to include the analytics infrastructure in your current infrastructure that you just showed me, right?
So you mean, let me see. We're asking about, like, basically there are two components in our infrastructure. And then we added a third one that is Flannel, that is, we place it in between user and the web app.
Oh, okay, I didn't explain. So you have all these messaging infrastructure and reliability infrastructure, but at a certain point you need to include the analytics infrastructure. Is the infrastructure the same, or is it mixed in all of these that you have just shown?
It is integrated into every of our services.
Okay. I was just curious if this was just for messaging and you already had a different infrastructure just for analytics that connects to the current infrastructure that you shown here. We'll talk about it later. Don't worry.
Does anybody have any more questions?
Hi, thank you so much for the talk. My question's about when you solved the first issue regarding the lazy loading, your solution. And I was wondering if there were any unforeseen consequences or challenges between switching from an approach where you send all the data, all of a team's data to the user, and sending him just specific channels that he's in and relevant information for him. So I was wondering if, when you made that switch, if there was any consequences of not delivering all the data immediately, and how did you deal with those?
There's no such consequence. So actually, it's not a one step. It took us almost 1 year to do the full switch. We first, so for Flannel, you're asking about Flannel, right? So Flannel, first, we only put users' data into it. And we test it out, we prototype it, and we decide it works. Then we have a gradual rollout. We first rolled to our own team. Like we also use Slack for our own communication. We fully test it, and then we roll out to all users. Then we moved more objects into Flannel service. Like we moved channel objects. We also moved membership. Then we moved like user group and more and more. So it's a gradual process.
Okay. Okay, that makes a lot of sense. Yeah, thank you.
More questions? No? Let's give a round of applause, please.